What happens when a 30-meter deep excavation collapses, swallowing a major highway, costing millions of dollars and resulting in a tragic loss of life? The forensic investigation usually points to a single terrifying truth. The engineers believe their own linear models. A model assumed a perfectly rigid boundary where a highly non-linear, soft softening reality actually existed. The math was flawless, but the physics were a fantasy. Hello everyone and welcome back to Strong Foundation Engineering. In our previous video, we deconstructed the mathematical anatomy of FEA under the comforting assumptions of linear mapping. Today, we have to wake up from that linear dream. Recall our fundamental linear equation. Force equals stiffness times displacement. In a nonlinear world, stiffness changes as the structure deforms. We must acknowledge that the global stiffness matrix is not a constant. It is a live state-dependent operator. We can no longer solve for displacements in a single mathematical step. Instead, we must deploy an iterative search engine, like the Newton-Raphson method, hunting for the exact state where the residual force vector vanishes. To do this, we define the tangent stiffness matrix on screen as the Jacobian of the internal force vector, the instantaneous slope of our load displacement curve. When the solver fails to converge and diverges, what is it actually telling us? You need to train your engineering intuition to distinguish between two terrifying possibilities. The first is numerical divergence. Here, the math is simply lost. A load step was too large or a contact pair hasn't closed yet, creating an unconstrained rigid body motion. The second is physical divergence. The structure has passed a critical limit point, like buckling or massive plastic yielding. The matrix cannot converge because the physical structure can no longer find an equilibrium path to sustain the applied load. This physical nonlinearity bifurcates into two distinct phenomena. Let's start with geometric nonlinearity. Even if the material stays perfectly elastic, large displacements fundamentally change the structural behavior as axial loads ramp up. The geometric stiffness matrix actively erodes or augments the linear elastic stiffness. This is exactly where we account for p-delta effects, membrane stiffening, and large rotations. The tangent stiffness matrix becomes the sum of the linear stiffness matrix and the geometric stiffness matrix. The geometry itself becomes an active participant in structural resistance. The second phenomenon is material nonlinearity. Here, we witness the shift from the predictable, linear, elastic material matrix to the elasto-plastic constitutive matrix. We must introduce the flow rule, yield criteria, and understand how material softening or hardening fundamentally alters the local stiffness. When a steel beam yields or soil enters a plastic state, the local stiffness degrades rapidly. This localized softening triggers our next core concept, stiffness negotiation. But to understand how load redistributes, we must first look at the boundaries. In our previous video, we assumed boundary conditions were cleanly binary, either perfectly fixed or perfectly pinned. In nonlinear reality, boundaries are almost always contact problems or nonlinear springs. Supports are highly sensitive. If a support deforms, soft softens, or if a structural gap opens or snaps shut, the global matrix undergoes a radical, instantaneous, and discontinuous change. To enforce these hypersensitive boundaries without crashing the matrix, solvers use penalty methods, acting like incredibly stiff springs or Lagrange multipliers. A slight miscalculation of this interface stiffness can lead to an entirely inaccurate failure mode. Unlike a static assembly, a nonlinear structure lives through its history. The load distribution strictly follows the evolving tangent stiffness path. Introduce the concept of stiffness negotiation, or what I call the hot potato analogy. When a specific structural member or localized volume of soil yields and softens, it can no longer carry additional load. The global matrix must force a redistribution, passing the excess load off to its neighbors like a game of hot potato. If the neighboring components are highly sensitive, brittle, or already maxed out, this negotiation fails completely, triggering a progressive collapse. Now for the professor's warning, the objectivity crisis. When modeling strain-softening materials, the FEA solution can become pathologically dependent on the size of your elements. In highly sensitive strain-softening soils, like the notorious Calling marine clay, failure zones naturally localize into razor-thin shear bands. Without advanced mathematical regularization, refining your mesh simply forces the software to compress all the damage into a single layer of smaller elements. The takeaway? A finer mesh without a physical length scale parameter doesn't give you the truth. It simply provides a highly precise, highly dangerous wrong answer. We have traced the journey from the rigid, static global matrix of our previous videos to the fluid, iterative, boundary-sensitive reality of today. We have watched how the tangent stiffness matrix approaches absolute singularity when local stiffness negotiation breaks down, but equations on a chalkboard only take us so far. What happens when the boundary condition sensitivity of a massive strut-to-Weiler connection is ignored in a 30-meter deep excavation? What happens when a model assumes a linear, rigid boundary? where a highly nonlinear, soft softening reality actually exists. Next video, we take these mathematical realities to the streets. We will apply every single one of these nonlinear principles to the nickel highway collapse. Subscribe so you don't miss this forensic masterclass.